Greetings, physics enthusiasts. Welcome to AP Physics 2, Unit 5, Lesson 4. So we are continuing our study of magnetism. And in this video, all I want to do is a couple example problems to show you how I would use some of the ideas and some of the equations that we've talked about already to solve some problems. So here is problem 1. I got to fold my little piece of paper so we can only see one of the problems at a time. So here's the first problem I want to look at. Let's see if I can zoom in and make the problem bigger. We have 4 long parallel conductors. So we have 4 wires, each carrying a current of I equals 5 amps. So these dotted lines represent, no, these dotted lines do not represent the wire. Here's a wire A, here's a wire B, here's a long wire D, here's a long wire C. So we have 4 long wires, kind of like this, you know, they're like this, like the posts for a fence. The direction of the currents is into the page at points A and B, hence these little X's on the inside, meaning into the page, and out of the page at points D and C, hence these little dots. Calculate the magnitude, meaning the size, the number part of the answer, and the direction part of the answer, of the magnetic field at point P, right in the center there, at the center of the square. And the edges of the square have length 2 meters. So I need to find the magnetic field created by this one here, and the magnetic field created by this one here, and the magnetic field created by this one at point P, and the magnetic field created by this one at point P. And I want to take those 4 answers and add them together. That's what this is asking me to do. Find a magnetic field, find a magnetic field, find a magnetic field, find a magnetic field. Where? There. And once I've found those 4 magnetic fields, I want to add them together. So the first thing you should realize here is that when I have a wire, and I'll show you the wire down here, when I have a wire with current in it, the direction my thumb is going, the field created by that points different directions at different locations. So this wire, if it has current traveling this way, over here creates a magnetic field that points into the page. Over here, it creates a magnetic field that points out of the page. Here, above the wire, the field points, toward the top of your computer and toward the top of my page. And here below the wire, it points toward the bottom of my page and toward the bottom of your computer screen. So when the wire is oriented this way, if the current is coming out of the page toward y'all, that's like points C and D. And the magnetic field points in different directions at different locations. So what I want you to do, copy down the problem, maybe press pause, copy down the problem, or the important parts of the problem. Don't write all the words, but draw the picture. And I want you to determine the direction of the field here, created by this wire, and created by this wire, and created by this wire, and created by this wire. And I'm going to tell you right now, it's going to be 4 different directions. This one creates a magnetic field here that points a different direction from these other 3 directions. So press pause, draw those 4 arrows. You could, draw 4 arrows here and label them B sub A, B sub B, B sub C, and B sub D. B for the magnetic field, and then created by those 4 different things. So press pause and do that. Go. Okay, and now you're back. Yes, if you're not back because you didn't press pause yet, press pause. So let's think about it. Let's start with C, just because it's easy for me to stick my hand over here. My thumb is pointing up. When I'm down there at P, the field points this direction, down and right. I'll call that B sub C. And wire D, above wire D, the field points left. To the left of wire D, the field points toward the bottom of the page. So over here, which is above and left, the field points down and left. This is B, the magnetic field sub D. Now, if you didn't understand that that's what I meant, you still have the opportunity to press pause right now and find the direction of the field created by these two. All right, now for these two, I have to have my thumb point down into the page. So for point A, when I have my thumb point down into the page, above the field points to the right, the field points down, below point A, the field points left. So here's point P is below and to the right. So the field points down and left, the same direction as there. So this says B sub B. It's actually B sub B comma A, both of those. I'm sorry, I can't read what I wrote there. That says D, B sub D and A. So these two wires create fields pointing the same direction, down and left. And then for B meaning between A and C, not B meaning magnetic field, the field points down and right. So I'm going to do C comma B. So if that did not make sense, I'm happy to talk about that more in class when I see you. But the idea is moving charge along a line is going to create a field that points in different directions depending on where we are relative to those moving charges. Moving charges create a field. All right, now I have two of these and two of these. Interesting. Two down and lefts, two down and rights. Do you see that these two left parts are going to cancel out these two right parts? And what I'm really going to end up with is just four down parts. So let's think about that. How strong, what is the number part of the magnetic field created by a current carrying wire? And that was an equation that we came up with. Oh, goodness gracious. I'm trying to look for my notes to tell you what video it was in. Here's my notes. So I showed you that equation back here in video number 2. Where is that? I'm not seeing it. Well, I will find it later and tell you where to go look for it. I'm going to pause and find it right now. I'll be right back. So I'm going to press pause. I'm back. It was in 253, the last video, the one you just watched before this one. So, and what is that equation? It is the equation that we said is called Ampere's law. B, magnetic field, equals mu naught I over 2 pi r. I can't remember if I use capital or lowercase, capital R. So it's called Ampere's law because it's really important. Again, we talked about it in the previous video, but it's a big deal that moving current creates a magnetic field. Moving charges create a magnetic field. So they tell us the current is 5 amps. Mu naught, I'm going to look up the exact value that they want you to use from the back of your book. And 2 is a number, pi is a number, and then r is going to be this diagonal distance, how far away we are. If this distance is 0.2, then this distance is 0.1, and then this distance is 0.1 times the square root of 2. if I have a triangle that's isosceles and right, it has sides of length A, and A root 2. You should remember that from your math class. If that's not obvious, ask me in class and I will happily do that derivation for you. All right. And so now R is 0.1 root 2. 0.1 root 2. And I was going to look up mu naught in the back of your textbook. 1.26 times 10 to the minus 6th. 1.26 times 10 to the minus 6th. All right, so this is just a bunch of stuff, and we can get some number. It's a magnetic field, so it's a number of Teslas. Now, that is not the answer to the whole problem. That is how strong the magnetic field each of these four is. So let's do that quickly on our calculator. 1.26 times 10 to the negative 6th. I is 5. And then divide by 2. And divide by pi. And divide by 0.1. And divide by the square root of 2. And I got 7.1 times 10 to the minus 6th. 7.1 times 10 to the minus 6th. Now I did a bunch of calculatoring there. So usually when I do a bunch of calculatoring, I put the numbers in 2 or 3 times and make sure I get the same answer every time, just to make sure I didn't press a wrong button. So I would suggest that for you. It's worth your time. Especially, if I got that wrong, that would be great. If I press the wrong buttons, it would be making that point. But now, so I have these 4 arrows, this one, and this one again, and this one, and this one again. And this is the size of each of those 4 arrows. So each of those 4 diagonal arrows has a down part and a horizontal part. And this horizontal part and this horizontal part cancel each other out. So I'm really just looking for this part, and I'm going to multiply it by 4. So this is 7.1 times 10 to the minus 6th. And this is a 45-degree angle. So this is 7.1 times 10 to the minus 6th times the sine of 45. And I'm going to take that and then multiply by 4. 7.1 times 10 to the negative 6th. And then I'm going to multiply by sine 45. And then I'm going to multiply by 4. And that should be my answer. 2 times 10 to the negative 5th. So that was our first example problem. Wouldn't it be a great idea for you to go back to the beginning and see if you could do the whole thing now without my help? All right, for the second problem, it's right here on the same piece of paper. I just folded it in half. It is desired, we want a solenoid, lots and lots and lots of loops of current carrying wire that will have a resistance of 5 ohms. Well, that makes sense. A solenoid is a lot of coiled wire, and wire has a resistance. So they've told us the resistance is 5 ohms. And we want it to produce a magnetic field inside of 4 times 10 to the minus 2 Tesla when it carries a current of 4 amps. Boy, that's a lot to hold in our heads. Don't worry, I'm going to draw a picture. The solenoid is to be constructed from copper wire. Okay, so the wire is made of copper, and copper wire with a diameter of 0.5 millimeters. And the radius of the solenoid is 1 centimeter. That's a lot of details. Determine the number of turns of wire and the length of the solenoid. Okay. So you could put it on pause and try to summarize this if you want, or you could just watch me. So here's what I'm going to do. I'm going to set this. I wish you could see both. Maybe if you can see that there, and then my paper over here. All right, so we want a solenoid, which looks like this. Loops and loops and loops and loops of wire. And it's inside here in the center that I get this magnetic field when current I is flowing through the wire. And so they told us that they want R, the resistance of this whole long wire. They want the resistance to be 5 ohms. Okay. And then they told us that the wire is going to be made of copper. So that's making me think of that equation that says resistance equals rho L over A. The resistance of a long wire is equal to the resistivity of the material it's made from, here copper, times the length of the wire divided by A, the cross-sectional area of the wire. So this wire, if I stretch it out and make it long and straight, it's going to look like this, where this is the length of the wire. And this right here, this is the cross-sectional area. That's what L and A mean. And they told us the resistance of the whole thing, and they told us the thing is made of copper. And they told us something about the edge here. What did they tell us? They told us the diameter was 0.0005 meters. The diameter here equals 0.0005 meters. They told us the diameter is 5 millimeters. That's 0.0005 meters. So they gave us this and this, and we can look up this. So really, we can find L, the length of the whole thing. Maybe that's necessary. I don't know. Well, I do. But anyway, so that's how you could think through that. What else did they tell us here? They told us the radius of the solenoid is 1 centimeter. This radius here is 1 centimeter, 0.01 meters. I'm changing everything to good units. And then they want to know the number of turns and the length of, they want to know this length, the length of the solenoid. So there's another length. This is a length, it's the length of the wire. I'm going to call that L1 so that I can call this the length of the solenoid L2. And they want us to find the number of turns N and the length of the solenoid L2. Notice that I used a capital N here, and we distinguished in the last video between capital N and lowercase n. Capital N is the number of turns. In this picture, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. That's just the way I drew it. And little n is N over L. Little n equals big N over L2. Little n is the number of turns per unit length. And if little n is a big number, it means it's wound really tight. And if little n is a small number, it means it goes, turn, turn, and it's not wound very tight. Okay, so now we have the problem and we have our picture of what we have. We have this wire wrapped up into this kind of a coil. The other thing that you might realize is that this length is going to be a lot longer than this length, right? This is the length of the coil. When I stretch it out, it becomes this length. Each turn, oh, there I go, 2 pi r. 2 pi r is the circumference. And then I go 2 pi r again, and 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 2 pi r again, right? So, 2 pi r 0.01. That's the circumference. And that times the number of turns, 1, 2, 3, 4, 5, 6, 7, 8, 9, times the number of turns gives me the total length of the wire. Oh, 2 pi r times the number of turns equals the full length of the wire, L1. Do you see that? Each loop has a circumference. And there's n of the loops, and the circumference plus the circumference plus the circumference plus the circumference, which is times the number there are, gives me this full length. So if I find n, I know L1, or if I find L1, then I know n. So now let's go back, and I'm just going to give you a moment to read the problem through again and see what you think it would make sense to find next. Press pause if you want more time. So based on what we're given, I think it would be pretty easy to find L1. We know 5. We can find A. It's pi r squared. We can look up the resistivity and therefore find L1. And once I know L1, then I know N, which is one of the answers. So how do you find rho resistivity? Little research skills. If you're in your textbook, we're in chapter 19. And in chapter 19, we study magnets. No, we learned about resistivity, back before when we were studying circuits, right? Oh, here we were in chapter 18 studying circuits. Look at the end, at the review there. No, there was nothing about resistivity there. Let's look back at chapter 17. And use that review at the end of the chapter. It's really, look, there's a section called resistivity in chapter 17, section 5. So I'm going to flip back to section 5, resistivity, and look at that. There's a table right there with resistivities of different materials. Copper, 1.7 times 10 to the, goodness gracious, I can't even, it's so small. 1.7 times 10 to the minus 8th. 1.7 times 10 to the minus 8th. 1.7 times 10 to the minus 8th. Now, I had looked that up earlier, so I have that written on another piece of paper already. But I wanted to show you how you can use the tools that the textbook gives you to find some things. Now, of course, these days, you can just use your phone. What is the resistivity of copper?
Here's an answer from Wikipedia. Copper has the highest electrical conductivity rating of all non-precious metals. The electrical resistivity of copper equals 16.78 omega m at 20 degrees Celsius.
All right, now this says 16.78, which feels like a much bigger number than this. But then it says nano. It uses that little n, which means times 10 to the negative 9th. So 16.78 rounds to 17. And 1.7 times 10 to the negative 8th is 17 times 10 to the negative 9th. So it gave us exactly the same answer. So feel free to use Siri or your Alexa or whatever. But if you need to use a textbook, there are easy ways of finding these things as well. Okay, so I'm going to say 5 equals 1.7 times 10 to the minus 8th L1 over A, which is pi r squared. And the radius is 0.0005 over 2 because they gave me the diameter. That's easy to solve for L1. And when you do that, you get 57.7 meters. So stick that into your calculator. L1 equals 57.7 meters. That's a long way. L1 is 57.7 meters. And then we just stick into this equation and we find capital N. I have this written down as well, 919. So you do the calculator part on your own. If you're having trouble getting these numbers to come out of your calculator correctly, feel free to ask me. I'm happy to help with that. Now, once we have found N, which is half of the problem, then we need to find the length of our solenoid. So we're going to use this equation from one of the previous lectures. B, the magnetic field inside a solenoid, I think it's from lecture 3. B equals mu naught Ni. I'm just saying that. I want to see it written down in my notes as well. Yes, mu naught little n, which is the turns per unit length, times I. Now, they told us what they want the magnetic field to be in this problem. Did they not? They want the magnetic field to be for Tesla. And we looked up mu naught already. Did I write it on this piece of paper or somewhere else? I wrote it on this piece of paper. 1.26 times 10 to the minus 6th. 1.26 times 10 to the minus 6th. N I. And they want it to be that when the current is 4 amps. So I've got a 4 there. So what I'm going to do is I'm going to find little n, and I'm going to use it, or I could just say little n is n over L2. But n is 919. Well, hey, everything in that equation is given except L2. So stick that into your calculator and you can find the correct value for L2. Make sense? I hope so. Those are my 2 examples for today. Let me know if you have a question about any of them. Have a wonderful day, but whatever you do, don't break the laws of physics.